Okay, so welcome everyone. I'm glad that so many of you came despite of the rain. So today we're gonna continue the discussion that we had last time. So let me briefly recall you remind you what we talked about. So we discussed the problem of radiation from emitted by a charged accelerated particle, and we looked at the problem from a classical point of view, where we looked at the basically solutions to Maxwell's equations sourced by a particle that had a kink in it. So sort of like a localized sort of like change in velocity. And we have seen basically that the radiation coming from it was described by some gauge potential that, roughly speaking, took this form. And then we have also recovered the same result from the computation of a scattering amplitude. And for simplicity, we looked at scalar QED, and we're going to continue doing this today. And this was just basically simplification in order not to have to carry around these spinners and like use these more complicated identities. But qualitatively, everything is the same in QED, and you can read about it in Peskin. But the idea is that we can recover the same kind of behavior, so the same Bremsstrahlung, by looking at an amplitude where we have there can be like a bunch of particles scattering, but in particular, we considered this sort of quantum analog of the classical problem where we have an incoming particle of 4 momentum p that scatters with some other stuff, maybe interacts with some probe, and then changes direction to some other outgoing momentum p prime. And we looked at the amplitude where we have a photon attaching to an outgoing photon because we wanted to look at the outgoing radiation. And this photon, we attached it to we summed over the two diagrams where the photon is attached to the incoming line and the outgoing line. And as we have argued last time, of course, in principle, you can also have this photon attaching to some arbitrary other legs or to some internal lines in this diagram. But we only focused on this case because, first of all, we have shown, or really, I haven't really had time to go through the full computation, but we argued that the leading contribution in the limit when the energy of this photon is very small, so goes to 0, comes essentially from these diagrams, as well as diagrams where the photon is attached to other external legs. But since we wanted to reproduce the Bremsstrahlung from just this kick, we just restricted our attention to these two diagrams, yeah? And so, and this can be computed essentially using the soft theorem. So I mentioned that last time. And these two factors are essentially the soft factor associated to the photon attaching to the two respective legs. And they multiply the amplitude that without the photon, okay? And then here there are some order q to the 0 corrections. So again, we are looking at the limit when q goes to 0. Or rather, since q is a null momentum, when the energy of the photon goes to 0. And so from here, what we last said like last week was that we can compute the probability of a photon to be emitted. And we have seen that basically that's given by the absolute value squared of this factor integrated over the energies of the photons. So say naively, you integrate from some energy k equal to 0 to some k max. And we can just factor out the energy from here. So the scale in this q, so integrating over, I'm calling it k, it's the same as the q here. We can factor out all of the dependence of these guys on the energy. And we end up with this logarithmic divergence in the limit when k goes to 0, times some other factor that just depends on the other angles involved in the problem and the hard momentum, so on p and p prime. Okay, so we have isolated the dependence of this amplitude on the energy of the photon. And it's very clear, so as I just said, so this gives a log of k max divided by 0, but in quantum field theory, we don't like, I mean, this is the divergence, and it comes from the low energy limit here. So one can regulate it by replacing that 0 to some k min. And then, so this is a logarithmic infrared divergence, also called soft divergence. And this other factor is independent on the energy of the photon. And furthermore, we have written this down explicitly last time, and we have taken a limit where basically in this ultra-relativistic limit, where the scattering energy is much bigger than the masses of the external particles, this thing also takes the form of a logarithm, and it's a logarithm now in minus q squared divided by m squared, where m squared is the mass of these particles, which is assumed to be the same, and this k squared is just basically p minus p prime squared. So it's some kind of momentum transfer kind of thing. So okay, so we have this double log behavior. This is also known as the Sudakov double logarithm, and it's at the heart of the infrared problem in QED as well. And unlike how you would deal with usual UV divergences, this thing cannot be removed by just adding local counter terms to the Lagrangian. So we have to deal with this problem somehow. And furthermore, here you may be even more worried, as we said last time, that we have a probability here of a photon to be emitted. This probability cannot obviously be infinite. Okay, so this is a puzzle. And so what is going on? So so the idea now is that we have kind of ignored one bit of information, and we hinted again towards this last time, namely the fact that the amplitude, so this amplitude by itself can also be infrared divergent. And in particular, if that's the case, you may hope maybe that somehow you should be able to, like, these divergences could somehow cancel after taking into account what's going on with the amplitude without the emission of the photon. And at the heart of this idea, or rather of what we are going to do next, is the idea that actually a particle, so in practical, so experiments, we always have a detector that detects these external particles. And in particular, the detector is always going to come with a scale attached to it, which is the detector sensitivity. So let's call this lambda. So lambda subscript d, below which it cannot, below which it cannot detect. So particles with energies below lambda d cannot be detected, okay? So, so again, here, this lambda d is going to be somewhere in between this k min and this k max. This k min was just an artificial infrared regulator. This lambda d, you can think about it as a more physical scale, right? It's associated with the device. And so, in other words, the process of emitting a photon with energy below this lambda d is actually indistinguishable from just the process with no photon at all. And even the emission of like an arbitrary number of photons, as long as the net energy that is emitted lies below the scale, is also indistinguishable from just one electron. scattering, no emission. Okay, so let's look at the, and so if we are interested in some probability, we want to sum over the basically probabilities associated with these two scattering processes. So one without the emission and one with one photon emission. And later on, we're gonna see how to incorporate basically an arbitrary number of emissions as well. So, so what about this process? So this is going to have, we have written it schematically through a diagram of this kind. But here we were agnostic to, so again, last time, and there was an exercise that basically didn't really matter what the details of this interaction were. And this low energy spectrum of this radiation was unaffected by that. So if we want to compute a process in the quantum field theory that doesn't have a photon in it, we'll need to care, but we'll need to sort of also think about what happens in the interactions. So let's look at that. So here, in principle, one can have like a sum over basically 3-level processes, 1-loop processes, and so on and so forth. So I'm just going to restrict my attention to the 1-loop computation, because you'll see that the idea is to show that that's also infrared divergent. And so when one computes the cross-section, the inclusive cross-section of this process together with the process of emission of one photon, the infrared divergences will cancel. So that is where we are going for. So here we have the following diagram. So again, I'm gonna do things in QED, and you may also be worried about diagrams where you have 2 photons attaching to the same point. I'm gonna ignore those for a moment. In QED, at 1 loop, these are the only really diagrams that you need to worry about at 1 loop, right? Because we have the photon always has to attach to electron lines, and sort of like really, in this case, scalar lines. So let's focus on this one. And again, we have a P prime and a P. And then there's going to be some. So this diagram, sorry, there is a 3 piece. I haven't written that down. And the 1 loop piece, or rather, let me write it in this way. So this at 1 loop, it includes a term like this. Yeah, and let's focus on this. And at each vertex, we have a factor of E. So this diagram is suppressed by 2 powers of E, the electric charge, compared with the 3-level diagram. And any higher loop diagrams are further going to be suppressed with respect to this one by increasingly higher powers of E. So this is order E squared times the 3 diagram. Suppressed by powers of. Okay, so this is what we want to calculate. And I should say that, so I'm going to do this in scalar QED using the Feynman rules that we've written down last time. But if you want to see the full computation in QED, you can check out chapter 6. I think it's 6.3 of Peskin and Schroeder. And the idea is that, so in Peskin and Schroeder, they do the full computation. You can compute this just exactly. And then they take an infrared, they show that the result is infrared divergent. So together, to then extract the infrared divergence, they take this full result that they obtain after a few pages of computation, and then they, they are able to like sort of resolve this infrared puzzle in a way that we'll sketch. But it turns out that if you're only interested in the infrared divergences, the computation can be actually drastically simplified, and this is what we are going to do today. So in the computation, so let's see how that goes. So let's look at that bit of the diagram that has the photon running in that loop. So I'm going to focus on this part. This is a different color. Okay, when you look at that, so this diagram, let's write it just that a bit bigger here. So we have incoming momentum P, outgoing momentum P prime, and then we have, let K be the energy, the form momentum of the photon in the loop. And then by momentum conservation at each vertex, here we need to have P minus K, and here we need to have P prime minus K, and then we also need to have here this Q equal to P prime minus Q. Yeah, and we can calculate this. And to calculate it, okay, and this is going to attach to some other bigger diagram. I'm going to restore that in at the end. So what we have to do, so here we have to integrate over the photon that goes in this loop. So we have an integral over d4k, and in particular, this is a virtual, right? It's a virtual exchange. So this k obviously is not on shell. We have to integrate over the full d4k divided by 2 pi to the 4. And then what we have to do, well, we have to put in the Feynman rules for the vertices and for the photon exchange. So there's vertices, and then there is the photon propagator. So for the photon propagator, we have minus I eta mu divided by k squared minus I epsilon, where I'm using the Feynman prescription as last time. And for the rest, for now, let me just draw a picture. So the remaining picture, I'm going to see in a moment that it's suggestive. So we have something like this. So I have basically broken down, I have cut this diagram into a piece that involves the propagator, and this diagram where we basically have two off-shell emissions, okay? So this is incoming K, here we have an outgoing K, so really minus K, and then the same other momenta that we have before. Q and P prime minus K. Okay, let me just not confuse you with the signs. Yeah. So at At this point, I'm observing signs that distinguish in and outgoing momenta in the definition of K, but I'm going to restore those in a moment. So at this point, the decomposition is exact. Importantly, these lines here are off shell. But now the main observation is that you can do some power counting from what you'd expect to get from these vertices in the limit. So we are interested in infrared divergences, I should say. So we care about the limit k goes to 0. So we want to see when does this integral blow up. And as you may be familiar from quantum field theory, you can just count inside the integral. So we have like 4 powers of k in the numerator. Here we have 2 powers of k in the denominator. And here we are hence interested in the piece, if we're interested in the divergences that come from the k equal to 0 regime, we should be looking for terms that are order 1 over k squared or higher that come from this diagram.
Can you pass the list of names? Yes, sorry.
And I should also say that, okay, so we're going to do a bit, so there's going to be a bit more algebra now, but afterwards it's going to be a bit more conceptual. So like you should feel free to ask questions at any point. So yeah, so we want to see terms that have poles 1 over k squared or higher in the limit when k goes to 0. Otherwise, it's not going to diverge at the lower k limit. But turns out that the leading ones from last time, as you take k to 0, you can now use essentially these soft sort of formulas that we had before, right, in that limit. For this diagram, it's these 2 vertices. The slight difference from like last time is that these lines are actually here off shell, but we can still, we are going to like write them down explicitly, and we're going to see that in the k goes to 0 limit, the leading contribution is essentially going to be given by 2 soft factors associated to those emissions. So let's call this, I'm going to go to the next board, let's call this star. This is what we are computing. The star is equal to, so I'm going to put in, and now you should, if you took notes, you can look at last time, just going to put in the vertices and the propagators for these internal lines in this diagram. So this is going to give minus e squared. There's 2 powers of e. There's 2 powers of ie coming from the vertices. And then we have d4k 2 pi to the 4 minus I eta mu divided by k squared minus I epsilon. And then we have 2p prime minus k mu 2p minus k nu divided by minus 2p dot k plus k squared, well, minus I epsilon, where the p squared plus m squared has cancelled because p is on shell while k is not. And here we have minus 2p prime dot k plus k squared minus I epsilon. Okay. And now we are only interested in the k goes to 0 limit of this. So I can Taylor expand both the the numerators, I can ignore this k, and in the denominator I can ignore this k squared. It's not because they're on shell, but because they're small with respect to everything else. And so this simplifies, and then now so as advertised, here you end up with basically a product of 2 soft factors of the form that we found last time. I should also say that I've been using, as I said before, I'm working in a convention where I'm absorbing it. So in and out momenta, they differ by a sign. I'm working in a convention so far where basically momentum conservation looks like this for all incoming and outgoing particles. But of course, we need to take care of those signs, especially for this K. So for the P's that are external lines, I'm not integrating over, so I can just keep them as they are. But for the K's, I'd better put in the difference between the fact that here I have an outgoing photon and here I have an incoming photon. So I'm going to account for that by basically flipping this sign. And also here, but it doesn't matter because there it gets canceled. Okay? So this is just minus e squared and then integral over d4k divided by 2 pi to the 4. And then we have here I can pull out a sign. So with that sign, I get a plus I eta mu nu divided by k squared minus I epsilon. And here I just have, I can also cancel these factors of 2 now, as we also had last time. So I have p prime mu p nu divided by p dot k plus I epsilon times p prime dot k minus I epsilon. Okay? So now if you recall from last time, we also saw some integrals of this kind. And usually, so what we did last week was to basically, we looked at the pole structure of this and we drew last time. It looks the same now. So if you look at the complex K0 plane, there are poles like this. Poles when K0 is minus absolute value K, and K0 is plus absolute value K. And then there is like 2 more when K dot P prime is equal to 0 and when K dot P is equal to 0. And when we studied, so we looked at these integrals when we studied the classical Bremsstrahlung, and we saw that the radiative contributions actually came from these two guys, from the poles in K squared. And essentially we can now evaluate the K0 integral and include all terms and whatnot. But actually, it turns out that actually the two contributions, first of all, the radiative contributions here, they turn out to essentially add up to give the real part of this formula. So I can also, just to simplify my life, I can look at the real and the imaginary parts of this formula. And indeed, later on, we're going to see that only the real part is going to be relevant for the calculation of the cross-section. So let me just take this shortcut. So the poles at K0 is plus minus K. And up to the real part of this guy. So let's call this integral V1. So let's focus on this. With so we'll see that only these will contribute to the cross section. So bear with me for a moment. I'm gonna get back to this point in just a minute. But now, yeah, so now I can bypass, doing these contour integrals. I can just take the real part. And the nice thing about that is that what's the real part? Where is this plus complex conjugate divided by 2. And because of the I here, when you do that, you are basically going to encounter a difference between 1 over k squared minus I epsilon and 1 over k squared plus I epsilon. So the real part of that function, e squared d4k divided by 2 pi to the 4 I eta mu nu divided by 2 from the real part, and then we have 1 over k squared minus I epsilon minus 1 over k squared plus I epsilon. And let me just basically let's ignore the I epsilon description there. P prime mu P nu divided by P dot k P prime dot k. Okay. And so this you may recognize as the definition of a delta function in k squared. So in other words, when you compute the real part, that puts the momentum here on shell. So this gives 2 pi I delta of k squared using a formula. Well, basically, it's sort of a consequence of this formula. Something like this. Okay, let me not, there is an n-dimensional version of this, let me not, sorry, yeah, sorry. No, it's exactly this formula, right? Because when you then bring things to the same denominator, you get 1 over k to the 4. So it's exactly this. What? Yes, I pi probably. No, just pi. No, you're right. Yeah, exactly. Yeah, and then this is 2I comes from 1. So, and then we also know that delta, so let me just do all the steps. So k squared is k0 squared minus absolute value of k squared. And this we also know what it is from a delta function identity. It's 1 over k0, absolute value of this, and then delta k0 minus k plus delta k0 plus k. So essentially, since here we're integrating over all k0, these two factors essentially add up to another factor of 2. And you get the end of the day. So now you can just do the integral over k0 using these identities. And you get the following. So this turns out to be equal to 2e squared integral over v3k divided by 2 pi to the 4. And then we have a pi in the numerator. I've canceled some factors of I. Okay, so 2k0. And then we have p prime dot p. I can just contract those two using the eta mu nu. And k divided by p prime dot k. Yeah, and then now k is on shell. Meaning that k0 is basically k squared. Sorry, absolute values. Yeah, I mean, here there are still 4 vectors here, but I need to keep in mind that k0 is related to the spatial part of k. And also, if you remember, so to put it even into a form that's a bit more similar to what we had before, if you remember last time, we also wrote down completeness. We introduced some polarization vectors, epsilon, associated to the photons that were orthogonal and complete. basically allows me to rewrite this as minus e squared divided by 2, sum over the polarizations lambda, d3k divided by 2 pi cubed, 1 over 2, 0, times absolute value of p prime dot epsilon lambda q, sorry, epsilon lambda k, divided by p prime dot k minus p dot epsilon lambda k divided by p dot k, absolute value squared, right? So essentially this term comes from the cross term, and the other two terms are going to be order m squared, and I am ignoring m squared terms, like we did in taking this ultra relativistic limit. So yeah, so this was for m squared much less than p dot p prime. So okay, so now this looks very similar to what we had before. So let's compare. Yeah, unfortunately, those formulas that we wrote last time, it would be nice to have them somewhere on the board so we can compare and contrast. But you should trust me that the difference between this formula and the one that we found last time when we computed this, basically the probability to emit a photon, they just differ by a sign and by a factor of a half. Yeah, so let's put everything together and see like why those factors are exactly what we need to get the cancellation in the observable. So what is the observable? So now we have, I think, all the ingredients to put together to compute our observable. So the observable is, so this is just an amplitude. The observable is a cross-section. And it's a cross-section where we sum, it's an inclusive cross-section associated with just the process itself, plus the process with the emission of one photon. So I'm only computing it to one loop. So the subscript, I explained last time the difference between inclusive and exclusive. So here we are computing cross-section for the emission of one gamma plus the cross-section for no emission of the photon, but with a virtual exchange. I'm going to put the subscript 3 and virtual. Here, it's going to become clear in a moment what I mean by that. So, so this is something that we can can compute from the information we have today. So this is just the absolute value squared of the amplitude of this amplitude with no photon. Yeah, and to one loop is just given by this. So this object in general, so it's something like this. So let me draw pictures. Plus Yeah, this is how I'm just loop expanding my endpoint amplitude involving this p prime. And then I have to take the absolute value of that whole sum squared. So when we take the absolute value squared, first of all, we notice that any terms involving this would actually give order e to the 4 or higher in the cross section. And so we only care about, we want to look at the cross section to order epsilon squared, to order e squared. And so we only need these two bits. So we have absolute value of p prime. And then we have plus. And then when you take the cross terms here, what you end up getting is twice the real part of essentially this this amplitude that we just computed times the absolute value squared of this guy. So you can think about it for a second. So 2 times the real part of V1 times, again, this guy, basically the tree level bit. And then everything squared is going to be order e to the 4. Yeah. So just because the thing we just computed, it was only this bit, right? So we just extracted the coefficient, the real part of this coefficient in this calculation that we did in the infrared limit. So the infrared divergent piece of that, but you still have, I mean, this can be a complicated amplitude on the other side, and this is why we have the other, we'll have the other piece here. And the product of those two, this times complex conjugate, so this is why you get the real part here and absolute value squared of this amplitude. Okay, and you can just, so with this result, you can just plug it in, and it is the following. This is just this, and then from here, it's twice the real part, so this factor of a half cancels. So we have minus e squared, and then sum over lambda integral d3k 3 pi cubed 1 over 2k0 times p prime dot epsilon k lambda divided by p prime dot k minus p dot epsilon lambda k divided by p dot k absolute value squared. I just copied over this thing we just computed. And I also have introduced here a cutoff because this computation only holds for energies k that are smaller than some soft hard, if you want, factorization kind of scale. So this is some below which this approximation holds. So it's tuned, but again, the lower limit is just 0 right here. So in particular, this thing is going to be infrared divergent. So yeah, so what we observe from this virtual cross section is that first of all, only the real part of V1 enters, which is great because this is the only thing. In principle, there were other contributions to this answer that we argued that they can be ignored because they won't enter the observable. So it's great because, as you saw from there, this is the only thing that contributes. And then what you also see is that when you compute the cross section, actually one factor of a half canceled. So which is also quite nice because we want to now add up basically the other contribution from the emission of a photon. And to get the two, the infrared divergences from the two to cancel, we want the three factors to exactly match, right, such that this is possible. Okay, so then the sign, there is still a sign between the two, but of course, the punchline is that that sign is exactly what's needed to make this object, what is it, this inclusive cross-section to one loop infrared-finite. So yeah, so putting everything together, sorry, course of saying. So explicitly, we have, what do we call it, one loop inclusive. It has this part, virtual one gamma tree, and it's just this minus this thing. So from here, this is that. So E squared, sum over lambda. Okay. And then we have the thing from last time. So this thing is plus E squared. Ah, sorry. And of course this, I forgot to add here. Sorry. This is just the vertex function that we computed, but this gets multiplied, right, by the tree level amplitude in the cross section. Times. Yeah, and then from last time we had the same thing, basically up to a sign. Exactly after the same thing. Times the tree level amplitude. Sorry, I just noticed that the color is not great. Apologies about that. But yeah, but the key point is that, yeah, there is the sign. These things are exactly the same. So the bit that goes to 0, so that thing that the divergence comes from the lower limit of integration here. But when you take the difference between those two, that cancels. Okay, and yes. Ah, here. Yeah, so that cutoff, no, it's not the UV cutoff. It's relatively small scale. So, you know, when you use this so-called method of regions, you can isolate the IR like sort of the low energy part of a diagram from the high energy part of a diagram. Yeah, and it's sort of the scale that allows, you know, to do that. So in other words, I should say, so it shouldn't necessarily, you shouldn't confuse it with this, so previously I talked about the detector lambda, but really the scale also enters in this other bit that we have. So at the end of the day, it should cancel. Yeah, but the point is that in the coefficient, now the integral is manifestly infrared finite. And the thing about the detector sensitivity, and again, apologies about the notation, it's not this lambda, really this K max here, right, should be thought of as lambda detector, because this is the energy, it's related to the energy of the emitted photons, and it should be chosen to be the energy below which I cannot detect any photons. This is why I'm adding, why I'm computing this cross section that involves soft emissions, right? I wouldn't be, if I take this to be too large, then this calculation I'm doing doesn't exactly make sense, because then the line with no emission is not indistinguishable anymore from the line with the emission. So basically, this integral from 0 to k max from last time, when we computed the probability of emitting one photon, gets replaced by integral from lambda to lambda detector. And in particular, there is no more. And this also sort of resolves, well, to one loop order, which is what we have shown so far. It also is a way to deal with the infrared divergences that would come from virtual photons that are exchanged in loops. Because there, usually in QED, we don't compute inclusive cross sections, we compute amplitudes. And this amplitude, for example, for two electron scattering, is naively infrared divergent. The point is that once you take into account this inclusive cross section and allow for the emission of photons, at the end of the day, you get an infrared finite answer. Yeah, so the upshot is the final result doesn't depend on this lambda, which was this artificial cutoff that we used to isolate the infrared divergent bit from the finite bit or UV divergent bit. And then however, the result does depend on the detector sensitivity. And in some sense, that is regarded as a physical scale. So what is the time? So I'm not sure. Do you think it's better? I just had to say one more, like sketch how this works to all loop orders. I'm just going to draw some pictures, and then we can continue in the next hour, or we can also do this. Do you guys think it's a good place to pause? And okay, let's take a break actually. So we'll discuss the n loop case next hour. Great. Okay, so let's see. So now the rest of today's lecture is going to be a bit more like, as I said, conceptual. So let's now try to understand. So what we have seen so far, so let me summarize because there's been some questions. So what we are doing, what we have done so far is to compute the cross section for a process that involves n particle scattering. So one such example would be a 2-to-2 scattering process where you have an electron-positron pair going to an electron-positron pair. What we have seen is that that process is infrared divergent due to the virtual exchange, and this is what we computed last lecture. However, what we have also said is that this infrared divergence, what we noticed is that this infrared divergence actually can be cancelled by adding to the cross section for this 2-to-2 scattering process the cross section for a 2-to-3 scattering process, where the third particle in the final state is actually a photon that has energy below the detector sensitivity. And the cross sections for these two processes, these two, what we call sigma virtual and sigma 3, sigma virtual 0 gamma and sigma 3 1 gamma, the infrared divergences in these two bits come exactly with the opposite sign, such that the final answer for this inclusive cross section is finite. So actually, in QED, and there's been some great questions, and one of them was, what about higher loops? And indeed, in QED, this carries through to all loop orders. And this was demonstrated in a beautiful paper by Weinberg from the 60s, which is called Infrared Photons and Gravitons. And the nice thing about this sort of derivation and this paper is the fact that it carries through to all loop orders, and really all you need to know is the soft theorem. So this result for the Bremsstrahlung, for the emission of a photon that has some low energy. That we this classical result that we computed last time. So the way this works is like this. So if I look at the process, so let's consider now a process where we have the scattering of n particles. So if I take 2 particles to be in my final state, this would just be electron-positron scattering. So here we call this P and P prime, but I can allow for, I'm not going to care about this part of the diagram for now. So we have seen that actually to all loop orders, there's going to be exchanges that come from this sort of interaction here. So we can expand this perturbatively in loops. So we have a bit that is just the tree level on one side. So it's not going to matter. Again, I'm not going to care about what's happening here. We're just going to look at infrared divergences coming from the side. So this is a tree bit. Oh. And then there is going to be a one loop piece, which is the thing that we just looked at. But then you can also have other things. So for example, so if I'm only looking at processes that involve this P and P prime, so again, I'm restricting my attention to such processes. In general, you'll have to consider basically like attachments of these internal lines from between all external legs and whatnot, and do like a lot of combinatoric. I mean, not a lot, but like a little bit of combinatorics. It's still going to work out. So this is why has done it for arbitrary scattering of like n particles. Here I'm just going to look at this this one side of the diagram. So the other thing that you can have something like this, but then you also have to sum over. So for this two loop thing, you need to sum over bits where these photons are crossed on both sides. So you have to include all of the diagrams. So there's going to be a bunch of other diagrams at each loop order, but roughly speaking, they will look like this. And here you'll want to sum. Here you'll have like n loop There's going to be even more crossings, but you can actually relate all of them to just these simple ladder diagrams by just doing some counting of the contributions, and then you just have to sum from n goes to 0 to infinity, right? So this is like a sum. Yeah, so you have to do this whole sum, but the nice thing, so you can already, again, you have to do some counting to actually show that what I'm going to say actually holds, like including the factors and everything. But just by staring at these pictures, you can kind of see that this looks like a Taylor expansion, right, for the exponential.
What about the more complicated, the ones that have like
Yeah, in scalar QED, there's going to be things like this as well.
I mean
Like I'm illustrating it for actual QED, not scalar QED right now. Yeah. Oh, sorry. No, you're totally right. Yeah, you mean things like this. Yeah. So those things you can take care of those, but it turns out that they don't. They are basically killed by LSZ. And so the things that end up contributing to the divergences are of this form. And this is argued by Weinberg, and it's also in his textbook actually. So he discusses actually all of these. Yeah. So here, unfortunately, I don't have time to explain all of those things, and I'm going to make a few comments about that in a moment. But I just want to say that, yeah, after taking into account all subtleties, the infrared divergences, the infrared divergent contributions that matter will take this form. And if you look at this, as I said, it almost, we would want to see if we can basically exponentiate this sum. And it turns out that this is the case. And roughly speaking, what you end up with is sorry, I should say n ladder diagrams, just two virtual n ladder diagrams. You sum them all up, and the result is an exponential of just the one loop exchange, which is exactly this vertex function that we computed last hour, times the tree-level amplitude. Yeah. So, and I should say, you have all the ingredients. If you're interested in this, you have all the ingredients to actually do this calculation. And I said, maybe I misspoke, and I said that this actually turns out not to be difficult. I mean, you just have to count the symmetry factors in those diagrams. And once you do that, you'll see that the sum just reorganizes into an exponential. And yeah, and we've already computed this one loop exchange last time. So it's really it's very simple. Modulo the subtleties that were brought up about other potential diagrams. But for these ones, yeah, it's simple. So first of all, okay, one thing that you notice already at this point is that we saw that the one loop exchange is actually infrared divergent. Now that it exponentiates, turns out to come with a minus sign. So you get an exponential minus infinity times this, and hence this thing vanishes. So it's 0 due to infrared divergences. Okay, this is not a great thing, but we have explained in the past lecture how to deal with this. So what we want to do is to sum over emissions that are indistinguishable um, from this process. So process. So what we get in this case, again with diagrams, hopefully it's more clear what's going on. So we want to compute an inclusive cross-section where this one has no emission, but it can have all loops in it. And then we have one where we have one emission, but again, all loops in it. You know, everything else has loops. And here again, you have to sum over all possible diagrams where you attach, like we did last time, the photon either to this p prime or the p. And then we have dot dot, and then we have a process where we have n emissions. And again, here you have to do some counting because you can attach these lines on different, you know, either on p or p prime, and you have to, again, figure out what that factor is. The nice thing about it is that this thing, again, exponentiates. So, so this is just the sum from n equal to 0 to infinity of inclusive, well, sorry, it's the whole thing is an inclusive cross section. So this thing is a sum over the cross sections with n photon emissions. Sorry, I should say this is not little n, this is the same n that I'm using. Yeah, it's just notation. Okay, and this thing, so let me write it here, gives actually also, so also exponentiate, so it gives an exponential of the one photon emission, the cross section for the one photon emission, times the cross section for our process that also involves this and you know, all virtual exchanges. I'm using, hopefully the notation is clear. So whenever I don't have, so here notice that this would be like a tree level bit, but whenever I have this blob, this means I'm summing over all virtual diagrams as well. So this is just combinatorics again. But you can exploit this result for one photon emission we computed already. And then, but fortunately, luckily, so we also have this thing. I just wrote it down here. So I can just take absolute value squared of this, right? This is just absolute value squared of this result. So this is emission times e to the 2 times 1 loop exchange times this tree level, oh, not tree level, but yeah, with no additional loops in attaching to p and p prime. And we have seen that these two, so this was an amplitude. When you take cross section, we have another factor of 2, and this was just the cross section, and we saw that those are equal up to a sign. And so basically, the infrared, and they involve some integrals, right, over the photons that are emitted. And the point is that the infrared divergences, or rather the zeros in here, they actually cancel among those two factors. So I should say, yeah, these exponents here are equal up to a sign and up to cutoffs. And hence the result is infrared finite. Well, rather the result is not vanishing. It's finite order by order in perturbation theory. Okay, this is pretty nice. Yeah, equal up to a sign. Yeah. Yeah, these are exactly the things. This is the thing we computed last time. This is the thing computed this time, and we saw when we looked at the one loop cancellation that they came with different signs. So here we just exponentiate those two and multiply together the exponentials. Okay, and to sum up, I mean to sort of also address. So last time we left with this puzzle, namely that we had the probability of emitting a photon be infinite due to infrared divergences. So how does that get resolved? Well, to connect to the classical result, turns out that we can reinterpret this quantum calculation, or really classical part of this quantum computation that we did last time, and sort of identify. So we can use it to not to compute the probability of emitting n photons rather than one photon. So probability of emitting n photons with energies k between our detector sensitivity and this infrared sort of like scale that allowed us to only look at the infrared divergences in the virtual virtual exchange diagram. So this was just the factor that we had last time. So it's, well, with the combinatorial factors now put in. Log lambda d divided by lambda times I pp prime to the n. So this is just coming from the nth term in the expansion of the exponential. And then this gets multiplied by e to the minus e squared divided by 2 pi squared log of log of, I'm calling it lambda d divided by lambda. So this bit is from virtual exchanges. From the cross section of the amplitude involving these resummed virtual exchanges. But this you can, so let's call this lambda. So you see here we have 1 over n factorial, lambda to the n, e to the minus lambda. So we see that Pn is 1 over n factorial, lambda to the n, e to the minus lambda. And this is a Poisson distribution And basically lambda here gives you the mean of n. So on average, the probability, on average, the expectation value of n, it turns out to be just lambda for Poisson distributions. And it's given by e squared divided by 2 pi squared log of lambda d divided by lambda times I tp prime. And this one is, the key thing is that this is infrared finite. And we also, if you remember, this is also the classical result. Yeah, in the first lecture, we computed the expectation value for n photon emissions classically. This is how you recover it from this quantum computation. Okay, so questions so far? I'm not sure if it's just been super confusing, super clear. Yeah. Sorry, I'm using the stupid notation. This lambda I'm here. Yes. This capital lambda is the scale. So when you have this loop integral from 0 to infinity, I can split this. I focused on the infrared. I mean, you can, when I computed the one loop virtual exchange, you could have just computed this integral directly, but I decided to just split it into an infrared bit and a UV bit. And we argued that the only contribution to the infrared divergence comes from this bit. So this lambda is just the scale which allows me to just single out the infrared divergences. Yeah, it's like it goes, I mean, in effective field theory, it goes under the name, like doing the split usually goes under the name of the method of regions, and this is an artificial scale. It should cancel at the end of the day. But the thing that's physical is this lambda d, which is the detector sensitivity. And it is the detector sensitivity that replaced our infrared cutoff. So other questions? Okay, you should have many questions. So you could, for example, be very, I mean, I'm not sure, maybe people are super satisfied now because we have like, it seems like we have just resolved these puzzles with infrared divergences. I should also say I'm just doing it for QED. Here it turns out that the story is very simple because the one loop result exponentiates. Roughly speaking, this is a consequence of the fact that the photon doesn't interact with itself. If you try to do the same thing in QCD, for example, it's much more complicated. And in fact, these infrared divergences are not completely like well understood in that context because these one loop, two loop, three loop, they proliferate the infrared divergences and they may spoil this exponentiation. So they are known to exponentiate up to, I don't know, 2 loop order or something like this. I'm not an expert on that subject, but there's people working on this kind of stuff and understanding these divergences in QCD from a formal point of view. And these things that appear in the exponential usually are related to Wilson lines, and there is some observables associated to those, and they're called cusp anomalous dimensions and so on. And there is a story. So here it's very simple. The story, we're gonna like go over it in just a moment, but yeah, again, in QCD and also in gravity, somehow kind of surprisingly, it turns out that the result is a bit similar to this, and you can find it in Weinberg's paper, despite the fact that gravitons interact with themselves. So you might imagine that gravity maybe it's more similar to QCD, but it turns out that it's a bit more similar to QED. Yeah, so okay, so you may think that yeah, okay, everything came into place nicely, right? Have these infrared, I mean, this infrared puzzle seems to be resolved in this way, and maybe you can hope that you can do the same thing for other theories. But you may still, I mean, maybe some of you are not, I'm not sure. Are people satisfied with this resolution? We can take some votes. Who's like, raise your hand if you are very happy with how things worked out so far.
Sure.
Yeah. So you mean what square? Are we talking about the fact that I'm computing cross section or?
No, it's just this square. Given it also depends on lambda, right?
Yeah.
Should combine and make it constant.
Yeah. Yeah. You're touching on a yeah. Good. Good point. Wait. Sorry. Just to clarify, what is the square that you're talking about?
So the cutting constant is square. Well,
This.
Yes, it's a random cutting constant.
Sorry. Okay, sure. That is one. Yeah, okay. There are UV effects, but regarding the IR, let me rephrase the question in terms of infrared divergences. Yeah, but okay, yeah, it's a good point that you should. No, but in principle, you know, like whatever, it gets renormalized, but it should still exponentiate like that. Okay, maybe you can say in QED we know that this blows up at some like high scale, and maybe nothing makes sense at the end of the day. Okay, let's assume that we are below, I mean, from an effective field theory point of view. Let's say we are below some like very high, like, I don't know, like whatever scale this thing break down. So from an effective field theory point of view, maybe, I don't know. So, okay, people are not really, they don't feel any feelings about this. So let me just, yeah. So first of all, the first thing that you maybe are, I mean, you might be uneasy about is that the derivation just involved basically, it was kind of a bit brute force, right? Like it's not super enlightening. This is the right, exactly. And if you feel like it's enlightening, I invite you to actually read Peskin and Schroeder, where it's done in a bit of a different way. Like the way I've done it, I sort of like hinted towards the fact that, okay, the soft theorem is responsible for this, and you can glue things together and just essentially use the soft factors, and this is why this works. Roughly speaking, I haven't done the count for you, but you have to still do it, even in that case. If you actually took, if you read Peskin and Schroeder, you will see that their approach is a bit different. So they actually compute like this one loop vertex function. And you know, it takes a couple of pages, as I said before, and then they extract and then take the infrared limit. And indeed, if you do this for the first time, you should be doing it that way, because there is a big assumption in what I have said, namely the fact that, for example, only these ladder diagrams contribute to the infrared divergence. So if you want to do it carefully, you really should take into account all the diagrams and yeah, make sure that, you know, the infrared contribution, if you can compute the result exactly, then of course you are guaranteed that when you take the infrared limit, you are going to project onto, you're going to capture all the infrared divergences. Yeah.
You saw that lambda fundamental region.
So no, that's the thing. I mean, here there is always, so this is only the bit, it always comes together with the amplitude, this tree-level sort of like amplitude that also depends on this lambda. So those scales should cancel actually in the final result. But the final result for the cross-section will still depend on this lambda d, on this detector sensitivity. Yeah. So yeah, so then the question would be like, why did it work? So it's almost like a magical cancellation. Another thing is that secretly, in this calculation, we had to introduce an observer. So you might or might not like this. If you're an experimentalist, obviously you always have some detectors, so it's very natural to allow for this. But if you are a theorist, and in particular, yeah, it's a funny thing, right? It's almost, you have to assume that you need to have some observer. They're stupid enough such that they're not able to observe photons of like energies less than some scale. You may imagine that some almighty, I don't know, like in the future, when we improve our detector sensitivity, we may lower this to like arbitrarily close to zero. And in that limit, we run into the same issue. So this doesn't resolve that problem. So here it's just a detector that cannot measure energies below this lambda d. In particular, if somehow with future technology, if you are able to actually lower this to zero, the problem is back. And you may not be very worried about this because you kind of know that maybe from physical point of view, we can never do this. But then I guess we should also, like, no one should think or like ever try to maybe like study quantum gravity, because there you can also argue that never going to be able to make detectors that are, that have sensitivities close to the Planck scale, like not in like million years. So I mean, it's a similar. So if you care about the quantum gravity problem, you should also care about this problem. If you don't care about that, then you should. I mean, it's fine also not to care about this.
But you always, there's a lot of things in field theory are like, okay, but this is unobservable, so like this can't be unobservable, so
Yeah, indeed. So that's the effective field theory really paradigm, right? Yeah. But if you care about but if you care about, I mean, quantum gravity, we hope that there is some UV complete. So that's what I'm saying. It's like you may care about that or you may not care about that, and that's totally fine. But if you do care about something like quantum gravity, you probably should also like start worrying about this. Okay, so let me not say anything more about that. But finally, I mean, you may be uneasy. So the final point I wanted to make is that really in this cancellation that we've seen, we sort of gave up trying to understand the S matrix. And this is because, yeah, the cancellation doesn't happen at the level of the S matrix, but it happens at the level of cross-section. And in particular, an inclusive cross-section. And if you want to try to make sense of something like, so really, we are still, if you really care about the S matrix, so something like even for a 2-to-2 electron-positron scattering. So you can say this is, if you care about making sense of this process, so this we have just shown that is e to the minus infinity. So this is 0. Okay. So, and also you may wonder, what about unitarity? This seems pretty like a pretty drastic result. Oh, sorry, just realized. Yeah. So, okay, I mean, this is probably the worst of all because we probably want to understand the S matrix. So we may imagine that to be useful, and we may want to also be able to understand S matrix unitarity. And so but of course, we also know that, so what we have learned is really that electrons cannot really like exist in isolation. So they really have to always come with some kind of Wilson lines attached to them. Yeah. Yeah, that's exactly the point we are gonna, yeah, exactly. So let's take, so indeed, let's take 3 seriously. So the fact that this amplitude for 2 electron positron scattering vanishes, let's take that result seriously because it's a result in quantum field theory, and there is many, we trust quantum field theory, and what it's telling us is that given what we learn is that given an initial state that has just an electron positron pair in it, the probability to end up with also a 2-particle state with no other stuff is basically 1 out of an infinity of possibilities, so 0. And this is not so surprising because, of course, in any scattering process, we do expect there to be infinitely many possibilities that you can end up with in the final state. And to cancel for this infrared problem, the only thing that's relevant so in QED, to add photons to the final state. So you may wonder, what about, I mean, you can also have an infinite number of electrons in the final state, but I invite you to actually check by drawing the diagrams that the diagrams that you'll get if you like add n electrons to your final state are actually not going to be infrared divergent like we have seen before. So they're not going to contribute infrared divergences of the form that we have seen before to the process. So final state, and so this means that we cannot just have, in the final state, we can have an electron-positron pair, but we can have an electron-positron pair together with a photon. And then we can have n photons, and really we can have even an infinite number of photons in the final state. So with this understanding, this kind of already suggests that maybe so usually when we compute amplitudes like this, we compute them in a basis of single particle, sort of like, multi-particle states that live in the Fock space. But given the fact that, one can, that actually in QED, so the electromagnetic force is actually long range, and electrons cannot really, even like, no matter how far you go in space and time, they cannot really be decoupled from their like photon-like clouds. This means that maybe one should revisit the basis of eigenstates in which one computes the S matrix. So, and indeed, it turns out that in QED, the infrared divergences disappear in amplitudes obtained by computing the S matrix in a different basis, namely a basis of so-called dressed state. So these have been since the rock. They have been introduced like 100 years ago. They go under the name dressed state, coherent state, Wilson line. Depending on the community you're coming from, you have surely have seen this in some way or another. And the basic example is that in QED, surely you have seen them in some class or relativistic, I don't know, even like electromagnetism or something like this, where you know that or you have learned that an electron by itself is not gauge invariant. But rather the object that is gauge invariant is an electron with a Wilson line attached to it that goes all the way to infinity. So something like so is gauge invariant provided that, and this is important, the gauge transformations have compact support in space-time. So this means that they fall off to zero at infinity. So the usual argument is like this. So in abelian, so I'm just restricting again, it's just abelian gauge theory. So we have this Wilson line multiplying this one particle electron state, and under gauge transformations, namely sending A to A plus B alpha for U1 gauge theory, we have, so the electron acquires a phase. This, remember, for gauge transformations, this is dependent on the spatial coordinates. And then we have e to the Wilson line, but now involving this shifted A. But this, I can just use Stokes' theorem here, provided that alpha vanishes at infinity, I pick up a factor of e to the minus. Sorry, I think I'm to have everything. Yeah, there is an I usually in physics here due to hermeticity. But yeah, so then we just pick up an e to the minus I alpha here. We have e to the I alpha from the transformation of the electron state, and we have a e to the minus I alpha from the transformation of the Wilson line, and then we have the same thing. And so these two cancel, and so we do have, so this object is indeed gauge invariant. And it's very important in this argument, again, I want to emphasize that alpha actually does vanish at infinity. So that usually we let the Wilson line extend all the way to infinity, because then in the argument, if you were to pick up a boundary term there, you would need to introduce some other, like some other particle that you would attach to it that would transform appropriately. And this is what they do, for example, in QCD. But anyways, so let's, this is the arguments go sort of like along these lines. And so Yeah, and so the things, maybe the things that we want to scatter is really like our states should look something like this, like not just pure electrons, but really electrons attached to Wilson lines, and just a different flavor of the arguments, in fact, from an independent. So this was, I think, due to Dirac long time ago, but similar a flavor, perhaps not necessarily connecting it to this analysis, but in the 70s, Kibble, Fadeev, and Kulish proposed a resolution. Sorry, I think also Chung has actually shown it, a resolution to IR problem for scattering amplitudes, where essentially what they argued is that you have to replace the asymptotic particle state. So for example, so here I'm just labeling it by a momentum p. So example would be just the Fourier transform of this electron state considered there. So you take this and you replace it by some dressing, what they call like coherent, and it turns out to be a coherent state of low energy photons. Where this cloud is depends on the momentum of this particle. And indeed, okay, more recently, sort of this prescription has been kind of understood also from a different point of view that involves analyzing asymptotic symmetries. So this is what I wanted to touch upon just briefly today, and then discuss it further next time, also moving on to gravity. So in particular, the RF for them was some integral over some momenta q of some function f, p and q times aq minus a dagger q. Sorry, these are all contracted. This is the formula that they wrote down, plus some order to the zero term, where the key thing was that this function has to have a pole in q. These are photon creation and annihilation operators. So this is just a coherent state of photons written in a way that makes unitarity of this object manifest. And in particular, for the cancellation, they chose this p mu to basically be the soft factor that we've seen before. So p is the external momentum of the particle that you are dressing, and then they chose it to be a function of this kind. And essentially, Chang has a series of papers where he, using this prescription that was sort of like argued for by Fadeev and Kulish, sort of using arguments based on the fact that, like asymptotically, the electromagnetic potential doesn't go off to zero, and hence the asymptotic states are not exactly free states. There is some interaction picture, there is a surviving piece in your potential that doesn't go to zero at infinity, and then they solved some Schrödinger type equation to sort of arrive at these sort of asymptotic dressed states. And then this was checked that if you actually compute, so if you take all of your outgoing momenta and you dress them with the appropriate coherent state, and you do the same for the incoming momentum, then this thing is infrared-finite. Yeah, and you can do it perturbatively. So sort of the argument is very similar, because you see as you start expanding things out, this object will sum over amplitudes involving arbitrary numbers of emissions that are now on shell. And you can, and then you can show order boundary perturbation theory that the same virtual divergences that always exist are now cancelled by these like photons in this cloud. Yeah, so this goes back to your question about, yeah, exactly. So the thing here was that, yeah, the fact that you can have states where you have infinite number of the soft photons in them, that takes you out of the usual Fock space. And what the stressing does is essentially like engineer some states that live in your, yeah. The fact that the usual picture, the S matrix, you can think about it differently, that the S matrix can be thought of as the conjugation of a finite operator by these dressings in the absence of, by some unitary operators that are e to the Rs. And basically, this means that the S matrix is not an operator on your usual Fock space. So to go back to the original Fock space, you also have to rotate your asymptotic state appropriately. Something along these lines. But you can read about it more if you're interested in this paper by Fadeev and Kulish, which, by the way, is not, well, it's not very easy to read just because of the way it's typed. But I believe there are some people who retyped this paper, so hopefully you can find that. Well, yeah. So, okay, but this may still, okay, and it turns out that you can actually relate. It turns out that you can relate this dress state prescription to these Wilson lines. In some sense, these things are related. There is another, yet a third point of view that you can take. And since okay, it's 40 past, so let me just say and then discuss this last time, that the prescription, so I should say that you may not be satisfied with this either, and indeed it doesn't. QED is a very special case in which this works, but if you try to generalize it to other theories, there are some issues. And I mean, all of these, I should also say that there's people working on them. It's sort of like they're not fully resolved. But what I want to do next time is to kind of, so again, this prescription is not, you may not find it very natural or convincing, but next time I'm going to show that you can make sense, or like rather give another point of view on why we needed these dressings by considering conservation of asymptotic charges. So the prescription is very natural if one allows for large, so-called large gauge transformations and studies their implications for scattering, for example. So this is what we are going to discuss next time, and roughly speaking, we're going to see that this prescription basically comes out from just demanding that these large gauge charges that we'll define next time are actually conserved in any scattering process. That will land you on this prescription on the nose. Thank you.